Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we're back here with the 20 watt Class A amplifier. There's been a few videos on this. There's a playlist down below, okay? At first it didn't give 20 watts. I tried a Class D amplifier and I came back. Well, I even did a Class AB amplifier, guys, so I'm going to show you that amplifier in another video. But I'm trying to get this thing done for a friend, right? And so I bought these boards that were finished, thinking I could put them in a box and do a few videos and have a kind of cool Class A amp project. Well, maybe it's turned into a better project because I've had to do a few things. So, but my friend's birthday's passed and he's kind of chomping at the bit to get this amplifier. Yikes. Okay, so in the last video, what I did is I was measuring some temperatures. I didn't really like what I saw, the temperature difference between the transistor and the heatsink right next to it. And across the four, I saw different temperatures and different temperature differences between that and the heatsink. So now you would expect there to be some differences. Towards the middle, you know, the heat's more congested. It's called self-heating. The transistors around them are heating up the transistor there and just all heating itself up. So maybe along the edge it'd be cooler, but I saw even more differences than that. Now it could be because of thermal lag. I didn't let it sit for say an hour, 45 minutes before taking readings. So it could be due to that. But you know, looking at the mica, I see a little blotchiness where the thermal grease is coming out. So I thought, well, I don't trust it. And I think I was trying to purposely ignore it before and just get this project done. But hey, let's just do it right, right? I hate to get in the box and the box just be too hot. So we might as well try to improve everything we can along the way. So, and then I ran out of thermal grease. So I got thermal grease, okay? So I'm ready to do this video. What we're going to do is, and by the way, I only have a few videos left to get this in a project, I think. We're going to mount these to the heat sinks. And then I've got a Bluetooth preamplifier. I've got several different preamplifier boards. I want to test them, see which ones to mate with this guy. And he wants to put a turntable into it. So I want to have a phono jack input. But also I think maybe it'd be cool to have a Bluetooth. So it'd be kind of like a Sonos system, if you're familiar with that. Or, you know, where your phone can play, you know, music through Bluetooth into the amplifier. That'd be cool, right? And then you can adjust the volume and all that way. So, so I got some cool videos to come up to kind of supplement this board and what we're doing here. Now, this guy here is mounted on the heatsink. We're going to take some temperature readings. Now, that heatsink is just a side of this box, okay? So, it's this side, obviously, and this board will go on that side, okay? And then, and the front plate is actually really thick, and even the top and bottom and back plate are decently, pretty decent thickness. I think that'll help pull the heat off the heat sinks and spread it around, and you know, hopefully dissipate that stuff. Well, all right, guys. So what we're gonna do is we're gonna come over here. We're gonna take some temperature readings. On each transistor, like on the metal base, and then on the heatsink along different points on the heatsink, okay? Just to see how well the heat's being distributed, you know, how well it's being coupled from the transistors to the heat spreader. And we have this bias transistor up here, which is really nice because as this gets hot, and he's mounted to the heat spreader, so we want him to be coupled to the transistors as well as possible, which I think he pretty much is, but we just want to make sure it's as good as possible, right? So what we're going to do is come over, take some temperature readings. We'll take off the transistors, unsolder them, unscrew them, take them apart, and there's some mica insulators, electrical insulators, right, between the metal case, which is hot. It's I think the drain or the collector. These are BJTs, and so yeah, you don't want them all shorted together on the heatsink. So there's a mica insulator in there, and so you know that thermal grease is not only trying to, you know, if it was just metal to metal, that'd be one thing, but we got to go metal to mica to mica to metal, okay? Now, guys, you don't spread that on there like cake frosting, okay? You know, I've seen some people talk about that and just say, oh, spread it on liberally. And then even to the point where, oh, when you push it down, it'll squish out. No, that's just way too thick. That stuff has thermal impedance too. I mean, imagine if you're doing a transistor can straight to the metal to metal contact is going to be the best thermal transfer. And then the air voids in between that, you want to fill that with something besides air, because air is not a good, you know, transmitter. You know, it's more thermal impedance than this thermal grease, right? So you put the thermal grease so it fills in those voids. That's the idea. Now between the transistor, which is pretty polished, and the mica, you need a real thin coat. And now between the mica on the other side and the heat spreader, I can feel a grain and I can see it. And you'll be able to see it when you bring the camera over. So I'll use a squeegee and put it on the transistor, you know, and on the mica that interfaces with this, and I might just spread it around on the metal and squeegee it and then clean it off after. I think I'll probably do it that way. Anyway, we're going to take temperature readings before and after, see if we can improve. Okay, let's do it. And yeah, it should be interesting. All right, guys, let me know what you think. And thanks for all your comments and everything. It's been great. And by the way, I've been kind of getting swamped, and I've been really busy at work, so my bench is a total mess. I kind of had to, I was in between things, projects, so I just decided to do this video real quick. So I've actually, it's probably going to take a couple of days to get it done. But anyway, yeah, so sorry about the mess. I'm actually really busy right now. So yeah, sorry about not getting videos out. Wife, you know, had a ski accident, had surgery on her knee, and tore some tendons and had to get them replaced. Anyway, so, and then we had family and visiting, skiing. So I had to go skiing with them, right? My wife couldn't. So sorry about the lack of videos, but we'll pick up the pace and get this amplifier done. All right, so let's bring the camera over and do this. All right, guys, so here's our setup for the temperature testing. I've got the side of the box underneath it right now. It's just laying on top of it kind of flush, but it's, you know, you can tell when it's mounted it's going to be a lot more, you know, it's going to be mated much better, and I'll have thermal paste, all that kind of stuff. So we don't really care about that right now. This is just going to help us keep the heat spreader here a little bit cooler. What we want to do is, I got a thermocouple right up on the TO3 mounting pad, you know, the base, and it's kind of up in between the screw and the base, and the other one is right next to the mica here, and I got a little monkey poo on them. So this is T1 and that's T2. And what's neat about this amp probe meter is it has this double input. So I can go T1 minus T2, which is 4 degrees. I'll show you T1, the transistor, 21, still a little warm. I've been running them, I was just letting it cool off, but T2 I think is sitting at ambient now, so maybe just slightly above ambient. Well, no, that's about ambient. Okay, and then what we really care about is the delta between those two. Meanwhile, I'll use this thermal probe just to go around, and you know, that TO3 metal can I can't really touch, but I can touch the tops of the cans, and I can touch the heatsink, and I can show you how the temperature kind of changes across this heatsink or this heat spreader. So some of these transistors I think are mated better. They might not be perfectly running in parallel, but I don't think that's the thing. I think it has to do more with the thermocoupling. I can see a little bit of white paste in some corners, but it doesn't look evenly spread. So I think they probably put them on pretty quickly and probably didn't do as good a job as they should have. So that's the theory. So let's go ahead and turn it on, and I'll show you the temperature there, and let's see what happens. Okay, I've got the FLIR over here, and I'll use the FLIR to measure this guy, And right now you can see that. And let me see, go to Fahrenheit. So there we are right now. And here we are, and it's just, all right. So what we're gonna do is, I haven't got, you know, this, I'll show you the temperature where it's sitting right now. Okay. This heat sink, I had it on for a little while, and it's been cooling off actually for a while, and so the temperature across this heat sink is pretty even right now. So let's go ahead and power it up. You'll hear the fan turn on, the power supply. All right, so I have 31.6 volts plus or minus on the power supply. Okay, and I have the 8 ohm 200 watt load, and I have 12.7 volts, so just about 20 watts, kind of max power. See, we're already got a 10-degree delta, so let's see what we are. Okay, this guy, the heat sink's getting pretty hot. This is 41 degrees here. Look at that, 43.8. And if I come over this corner, so 45. If I come up closer to the transistor, look at that, 48. Come over here, 50. You can see the heat sink just has, you know, it's not consistent yet. Eventually it'll soak up and the hot spots probably go away, but okay, top of this transistor is, look at 57, and then right next to it about 50. Then over closer to this transistor, so you got 53 there, 59, so about 6 degrees difference. But look at this guy, this one's a hot one, 66, and right next to it, it's like 50, 55 maybe. So it's got 11 degrees difference. And okay, right now we're at 70 on this one. And yeah, you can see the delta there, which this guy is showing us between those. So it looks like it's okay. Let's see if I can match what the Am probe is showing. 71.4. Yeah, so this, you know, these couples a little bit closer together, but yeah, you can see the temperature differences. 68. Okay, I'm gonna let it run a little bit longer. It's starting to get pretty hot though, but I'm gonna go ahead and write these down. This bias transistor will change the bias set point as it gets hot, so we'll set that up once we get a good running temperature and set the bias where it should be. But I just want to check the temperature difference right now, and to me it seems like it's gonna be kind of a pain in the butt, but I think I need to unsolder each one of these guys and check out the thermal paste, you know, maybe clean that up and apply some new paste. Okay guys, so first I removed all the hardware, all the screws from the transistors, and then I have to go through and unsolder each one. And I'm going to start with one of the two middle ones first, so I just use a solder sucker here to try to heat up the joint, and then that'll pull out a lot of the solder. These boards are pretty thick, pretty heavy solder, so it takes a little bit of heat. This guy feels like he's just about ready to fall out. I think it's just kind of stuck here on the sides. And there he is. So there's the first one. And you can see the, you know, they didn't. Here, let me flip it back over here. From this view, you could see that they got along the edge and there, and you can kind of see how it was on. It's up in this part, but there's not hardly any thermal paste down here. It's just kind of smushed up in this area here, so that's kind of what I was afraid of. Now see the little nylon inserts for the isolation? So here's one sitting here that came up with it, so I'll have to put that back in there. But yeah, this white stuff, thermal paste, gets everywhere. If you ever worked with it, it's a real pain in the butt. Now I got to be careful not to, you know, crack the mic because I want to reuse it. But uh-oh, look at this. Just a little bit on that side too. Now you only want a little bit, but you want it evenly spread. And there's nothing up around the hardware, so you can kind of see how it just didn't get, I mean, it's not horrible, but it's just not very good. So it should be better. There should be a little bit around here. So I'll take the rest of them off. We'll take a look, but I'll, you know, reapply. I'll walk you through it. All right, so this one came from this guy, this one, and that one. So I got them in order, and you can kind of tell, like, this pad here, this whole half didn't really have much, you know, really didn't have any thermal paste. It kind of only went towards the middle. So as a matter of fact, on this end of each one, it seems to be kind of thin. Oops, that mic, uh-oh, kind of chipped that mic on the corner, but okay, so yeah, you can see a little bit of goop there. It's just not, it's not, you know, like I say, it's covering it, but not as well as it should. And in fact, it might be kind of thick in certain spots, which what you want is just a really thin coating just to fill air gaps. The void, yeah, look at that. See how dry that is on this end? So there we go. They look like they could be better for sure, right? It's kind of dry right up in here. So yeah, look at that. There's some spots where it's kind of thick, and then there's thin spots, and then there's dry spots. This one's a little thicker in certain spots, and you can see this side of the mic where it mated with, you know, the heatsink down here. It just didn't do that great of a job, so we'll see if we can improve on that. Alright guys, this stuff gets everywhere. It looks thick on here because I got it on both sides, but you can see it on the transistor. It's just, I tried to get a little thin coating everywhere, and then when I put it down, I'll just try to wiggle a little bit, but it's kind of hard to do when you got two pins in. But you can wiggle it around just a little bit, just to hopefully, you know, hopefully it's even. This side I'll have to spread it around a little bit better. What I do is I'll put down a little bit more grease, and then I use the back of my ruler here to kind of just spread it so it looks like there's a really, really thin coating on. So yeah, I'll do that and I'll come back. Alright, and that's kind of what it looks like. Like I said, it looks thicker than what it is just because it's on both sides of the mica. And then I took my ruler and I tried to scratch off most of the stuff here. I just left what's in the grooves of the metal, because that's really those voids you want to fill up anyway. You see, you can see the metal there. I can kind of feel it too. It feels like there's lines, you know, kind of a grain going across this way, so alright, so that's kind of the technique I think I'm going to use. I've got the plastic inserts in. I'll have to make sure they're still in there when I push this transistor through. Alright, so I'll go ahead and snug up some hardware there and then do the other ones. Okay, so you can kind of see how I smeared it, trying to fill in some of this, you know, just that machining of the aluminum where it's just not really smooth. Just tried to fill in some of those grooves so that the thin coating I put on the mic will do a good job. Okay, I'm going to do the other three and I'll be back. Alright guys, so you might be wondering why we're going to all this trouble. And I just wanted to kind of show you electrical diagram. Actually a heat diagram. It's kind of like electrical, you know, you can look at it that way. We have our transistors, okay? And then we have our ambient temperature, the room. And in between there we have, you know, our heat sink and metal box and all that stuff, okay? So what we want to do in this case is we have these transistors and they have some thermal impedance inside them. So I've got all these resistors to show all the thermal impedance path and all the things in the path, or at least a lot of them. So in the transistor, the silicon itself, you know, just to get the heat from the die, the junction, to the case, the metal case in a TO3 can, you got your R theta junction to case, and that's shown by like a resistive element. And that's our resistance to the temperature getting from the junction to the case. So when we fill the metal box, we know that the junction of that transistor is actually a lot hotter because there's all these heat drops, like voltage drops, okay? So we get a heat drop here, and we can't do anything about that. But once it gets to the case, then we can use some thermal grease, and which I didn't show like all those things, right? But you know, we got some thermal grease to mica in that. So we got some impedance between the R theta from the case to the mica, and that's like the thermal grease. You know, that's how good of a connection we have. Okay, and then we could also throw in the actual thermal impedance of the mica in there too, if we, you know, wanted to. But what I'm showing is the things we can do something about: this thermal grease, the thermal impedance from the case to the mica, and then from the mica to the heat spreader, okay? And this is a heat spreader down here. So then that's some more thermal grease, right? So these are our thermal grease things, and these are the 4 transistors, and they all kind of are in parallel, and then they all heat up the heat spreader. So that's kind of what that's showing, okay? So we get all these little heat drops. So we measure the temperature on the spreader. You know, we know that every spot along the way is a little bit hotter until we finally get to the source of the heat. Well, what we can do in this case, we're going to try to see if we can get all these guys to all these impedances here basically to be equal to each other, and to also be as small as possible, so we get all the heat to the spreader as much as we can. And so it'd be great if the spreader was really close to the same temperature as the case. That's the ideal thing, you know, because once it gets to the spreader, then hopefully you can dissipate it out into the air or get rid of it somehow. In this case, we have the heat sink, right? So then we have some more thermal grease, some more resistance to the heat sink, and we want to keep that real small. So we won't just put the metal spreader right on the heat sink. I'll put a little thermal paste, a little thermal grease on there, okay? So we'll try to make that real small resistance. So the temperature of the heat sink and the spreader will be real close. Now just to let you, well here, okay, I won't get into all that stuff yet. Go off on tangents. And then once it gets to the heat sink, then it can go off into the ambient air, okay? And there's, you know, I'm showing some thermal impedance because I could say, well, also from the heat sink, I've got some impedance. I got another pathway to the rest of the metal box, the top and the bottom and the back and the front panels. So I can heat up all those things too, spread heat into those, and then off into the ambient air. But so pretty much from the heat sink, we start having, I could show parallel paths like this again. Okay, we got a parallel path from the heat sink, you know, all those fins right to the ambient temperature. So there's one path. Okay, then we have another one to, you know, to the top, and maybe another one to the bottom, another, you know, things like that. So we could add all these paths from the heat sink that it might be able to spread heat into, and eventually get it into the ambient. So there's 3 ways to, you know, to conduct heat. There's 3 pathways. I'm showing the conducted pathways. We conduct the heat until we get to here actually, and then from there we get rid of it in the other 2 ways. One is radiated, which is probably the least efficient. That's just, you know, just infrared radiation going off into the air, like exciting electrons around it. The other one is through convection, like maybe the air circulation in the room. It's going to move, just through movement, it's going to move, heated air particles around the heatsink. It's going to move them away and put cooler ones there that can get heated and, exchange air. Okay? So those are the three things: conduction, convection, and radiated. Radiated is the least efficient, but conduction could be the most efficient. But really, convection, if you can just blow air on these transistors, you could keep them cool. Or run, another thing's water, right? Water cooling, that's conduction. So, you actually have some metal that they're mounted to, and it's conducting it into the fluid and moving around. But anyway, all right, guys, let's get into our results, our test results. Alright, so just a little bit about the setup. Thermocouple 1, the black one, is on the transistor. The blue one, thermocouple 2, is just off the mic, real close. So we'll try to get real close there. And then I'll take this guy and take this little flat guy and move it around like I did last time and take temperature readings around the heatsink. Okay, the input signal's coming in here, and I'm monitoring it with this differential probe. On the output, we got our 3 voltages, our plus minus voltage with our return coming up here. I've got the output here being monitored with this differential probe, and the other differential probe right here, the green one, which is the ground. Okay, and yeah, so then the output going to the 200 watt 8 ohm load, it'll be monitored by this mixed sig, and then I'll have this mixed sig monitoring the actual current going into the power supply. So I just want to kind of look at those things. And all right, here, let me show you the rest of the setup here. All right, guys, so I'll be using the amp probe with this little cool setup, so I can do the temperature 1 minus temperature 2. It's kind of bouncing from 1 to 4 degrees, so it's pretty darn close. And over here we have the little thermocouple, the fluke thermocouple, into the FLIR meter. Okay, and then we have I'll use a Habo test. This is the same thing as Kaiweets, but I'll use this meter here to measure one of the voltage rails, just for fun, just so I can see it when I'm looking at the temperatures here, in case something happened. And if I'm not looking at the power supply up there, I can just happen to see it right here. Okay, I think I'm ready to start bringing up the voltage and checking the temperature. Okay, I'm going to go ahead and turn on the power supply. You'll hear some noise. Then I'll bring up the volume, or I'm bringing up the power. You saw the square go to the sine. Okay, there we are. And over here we'll see the temperature difference. And this is my little temperature probe. And there's the voltage we have on the power supply right now. So it's about 16 degrees ambient in here. On the heatsink down here below, about 16 degrees. So if I go on top of one of these transistors, see it get hot real fast. So what I'll do right now is I'll just go to T1. That was T1 minus 2, what we're looking at. Okay, it's 37 degrees. I guess we can let that heat up so we can watch it first. I'm just making sure those probes are pushed down there tight. Alright, we'll let this run and let it get nice and hot, and we'll come back. Alright guys, the delta on the difference between on the transistor is about the same or even worse than last time, but my one thermocouple is starting to lift up a little bit, so that could be why. But when I go around and measure here, I definitely get hotter temperatures. You see the FLIR shooting up right there? If I move it in right here, look how hot that is. So that is hotter than I saw before. So it looks like there's more heat getting spread to the heatsink than there was before. So here, I'll get a table together and I'll go over the results. But yeah, so there's all my measurements there. I just went around and touched each one of the tops of these guys. You can see now it's been sitting for a little while longer while I've been getting ready to do this, talk to you guys, so it's getting hotter. But I waited about the same time as I did last time and watched the bias current and everything. So, but yeah, okay, so let's go ahead and get together and I'll show you the table. Hey guys, I think that helped. I think it was worth taking the time to do that. Let me show you the numbers, but before I do that, I just want to thank the Patreons for supporting the channel, and all you guys for watching videos, supporting the channel, leaving comments and all that kind of stuff, and appreciate all that. Okay, so let's look at the board. This is that heat spreader, the metal heat spreader, and this is the bias transistor, and these are the 4 transistors across the heatsink, okay? And then I've numbered 5 spots on the heatsink that I measured, just to measure the temperature on the corners and in between each transistor. And this is what it is, Q1 through Q4, and then 1 through 5 here. And this is the before, B for before. Those are before temperatures, and this is the after temperatures. And I took 2 sets. What I did, I think in both cases, is about 15-20 minutes that it took to kind of stabilize the temperature. And also what I was watching is the bias current. As it gets hot, this bias transistor cuts back the temperature. And what was interesting is on the before, it cut it back to about 1.19 amps. Now again, I'm going to set the bias current, optimize it once we get all set up. But yeah, 1.19 amps, and then it kind of stabilized there. In this case, it didn't quite get to 1.19. It almost did, but then it hovered between about 1.21 amps. And in this case, I let it go a little bit longer, seeing if it would finally drop down to 1.19, and it kind of did, but then it would hover between 1.19 and 1.21 and go back up. What was interesting is because it was actually hotter in this last case, but still the bias current kind of wanted to stay up a little bit higher than it was in this case even. All right, so what we notice here is the temperatures here are in the kind of all over the place. That's one thing. They're not as consistent. That's why you saw in the last video. So 68 and 60, 2 transistors next to each other, 8 degrees difference. And then over here, we're the temperature, the heat sink was pretty consistent, around 50 degrees. But you can see the difference, over 10 degrees difference, right? And that's also what I saw last time. So in this case, we got high 60s, so it's actually hotter, probably because I waited longer. But then these spots here are in the, close to 60 or right in the low 60s. So yeah, it just seemed like the temperature difference between the heat spreader and the transistors is less here. It seems like the transistors are able to get the heat into the heat sink, which raised the temperature of the heat sink up, and kind of got things closer together. And over here, same thing. I went a little bit longer, and it finally heated up to this. Bias current didn't change, like I said, much more. And over here, again, it's like pretty consistent, 70s, and over here mid 70s. So about 5 degrees between these 2 cases. So it does look like what we did made a difference. That's awesome. All right, cool. All right, guys, that was worth doing, I think. Hey, thanks for watching, and we'll get back to this Class A video and get this amp in a box. Okay? All right, thanks for watching, and thanks for all your comments, and we'll see you next time.